An alloy is a modified metal, i.e. it's not pure, it's a mixture of different substances predominantly consisting of a metal. The purpose of an alloy, right, is to get the blending of different properties. So we can manipulate what an alloy looks like depending on what we want our properties to look like. They're generally harder, sometimes they're softer, but they're also less malleable. And we can use the metallic bonding model to explain why. Right, so it's made by adding a small amount of another substance. We melt them, mix them, and then cool them. Right? Fairly straightforward. Two types of alloys. One, substitutional. Substitutional, what word does that contain? Substitute. So what do you think that means? What does it mean to substitute? To take out and replace with something else, right? To swap. So what we're doing in our substitutional alloys is we're swapping some of the metallic elements with another element of a similar size and a similar property. So this is typically alloys that are a combination of two different metals. Our second type is called interstitial. Inter means in between. Right? So substitutional is to swap out. Interstitial is in between. So it's combining an atom of significantly smaller size that is able to fit within the lattice. They're generally stronger than substitutional alloys. If Iron Man and Silver Surfer team up, definition, yep. Interstitial is in between. I'll put up some diagrams as well. So a small amount of an element, significantly smaller atoms. I'll go through a couple of examples. Good. So if Iron Man and Silver Surfer team up, they become an alloy. Is that going to be substitutional or interstitial? Have a guess. You've got 50-50 chance of getting it right. Hands up for substitutional. Hands up for interstitial. Right, substitutional. Why? Right, they're both metals, right? So we would expect that their atomic size to be relatively the same. So let's open up a whiteboard. So substitutional alloy. So let's consider, here's my metallic lattice. Right, I'm going to combine something else. Okay, so we can see similar sizes, not quite the same though. We can see that some of those atoms or ions have been replaced by something of a similar size. What do we think with a substitutional alloy? What do we think in terms of conductivity? What do you think? Is a substitutional alloy likely to be more or less conductive than the original metal? Less. Why? Have a guess. You got your 50-50. Right, it is less conductive. Right? What does it mean for a substance to be conductive? Not what must it have. What does it mean? Particles can flow freely. So I've got ever so slightly different sized atoms, right? So ever so slightly different sized atoms causes, right, there to be an irregularity in the lattice structure. Right, and therefore increases the resistance. Yep. Substitutional alloys tend to be slightly more malleable and ductile. Reason for that being is that the lattice structure is not held quite as strongly together and allows us to manipulate the metal a little bit more.
Is this more malleable and ductile to the original?
To the original, yeah. So it's less conductive, likely to be slightly more malleable and ductile. Tends to have, well, both types of alloys tend to be more corrosion resistant. Okay, let's look at interstitial. So interstitial is in between. So there's my original metal. Right, and then we're actually going to put in atoms which are smaller. Right, tends to be more dense because we're fitting more mass into the same space. Again, corrosion resistant, slightly less malleable. So interstitial tends to be stronger.
More dense.
Slightly more dense, right? We're putting more material into the same volume. So examples of substitutional is something like bronze. Example of interstitial is steel. Right? Steel is an alloy of iron. So the larger atoms here would be iron, and the smaller ones there is iron and carbon. Stainless steel is something slightly different. Stainless steel would have a little bit of nickel, maybe a little bit of chromium in there as well. So it's actually a blend of both substitutional and interstitial alloys.
Yeah. Are they ever not just metals that are put in there?
Correct. So we might have something like sulfur in there. Carbon is a non-metal.
Would that be just for substitution?
Yeah, so sulfur is a larger atom. So sulfur would be an example of substitutional, even though the properties are not similar. But sulfur's more, allows for that little bit more corrosion resistance. The difficulty with something like sulfur is that metals can react with sulfur to produce metal sulfide. So something like fool's gold is called iron pyrites, which is a iron sulfide-based compound that has that goldy metallic look to it. But it tends to be brittle. It's slightly more dense than normal gold, and that's how we can determine its difference. Why is it not switching buttons? Okay. Heat treatment. Sorry. Treatment of metals. One is called work hardening. What does work mean? What does it mean? What does it mean to work? To do something, right? What does hardening mean? If I say harden up, what do I mean? Stronger, right? Have a little bit more resilience, okay? Right, so do some work, do something in which to harden up. So work hardening is a process which by we do something, right? Something physical. Work tends to be physical to harden a metal. So if we look at a metallic lattice and look at hundreds of atoms, we start to see that there's naturally some gaps in the lattice structure. Let's get the pointer. Right? Yeah, there's that. Come on. Naturally, we see there's some gaps in the lattice structure. So what we do is we take, say, a hammer. We would, say, slightly heat up the metal. Not much, but slightly heat. And what that does is loosens up the material. And then we'll hit that with a hammer. What that does is it forces the metallic particles to come closer together. And because metals are malleable and ductile, these particles will shift and fulfill those gaps. And we can see that those particles become closer together and we increase that regularity in our crystal lattice. And therefore it hardens the metal, decreases its ductility because we're reducing the gaps in between that lattice structure. Initially, it causes the metal to weaken because we might cause other fractures and other gaps elsewhere. But continued work, right? Heat it up, bang it out, heat it up, bang it out, will continue to strengthen the metal. So think about a blacksmith when we're talking about work hardening. That hitting of that object to harden it up. Heat treatment comes down to 3 processes. And it's our different ways of heating. Annealing, quenching. When you think of quenching, what do you think?
Drinking.
Cold, hard thirst. What does that phrase come from? Right? Have you seen like Solo ads?
Oh, Solo.
Harden thirst. You might have heard the word quench in relation to Solo, right? Quenching your thirst is to rapidly hydrate yourself. So to quench a metal is to heat it to a moderate temperature. Why would I specify moderate? If I heat up a metal too much, what's going to happen? It's going to melt, right? So we don't want to take it to the point where we're melting it. We're taking it to the point where the particles of the metal are loosened. Because you heat up something, increases the kinetic energy within the structure. So we heat it to a moderate temperature, so less than melting point, and we cool it rapidly. Causes smaller crystals to form as it cools rapidly. But there's large gaps between the particles, therefore makes it more brittle. But it's really hard but brittle. So we'll do a small prac on this next week. Annealing, right, is heating to a moderate temperature again, but we allow it to cool slowly. We have larger crystals and the metal becomes softer and more ductile. Tempering, you might have heard that in reference to chocolate. So when you temper chocolate, it's you heat it up, you melt it,